you are able to accumulate enough statistic or enough luminosity to see those events, then you can really extract information out of them. So that's, for instance, one example in composite model where you have, let's say, where the top mixed with some top partners, some vector-like fermions, so vector-like AV fermions, and then this mixing modifies the top Yukawa coupling, but those top partners can also run into the loop in such a way that actually the inclusive cross-section is insensitive to the mass of these top partners. So if you're looking at the inclusive cross-section, you won't notice that there is new physics. Right? But if you are now looking at this boosted cross-section with a PT of the X which is large enough, here I think this plot was made with a cut on the PT of the X at 600 GeV, then you can see that really there is new physics going on into the loop. So that's a good observable to resolve actually the details of the top loop. And that's also what is illustrated in this plot. So again, if you're looking at the inclusive cross-section, there is a degeneracy between the modified top Yukawa coupling and additional contribution to the loop diagrams, such a way that actually the inclusive cross-section is just telling you that you're sitting into the bound. And then when you add the information about the boosted cross-section, then you can shrink the bound to some ellipses. So you can measure individually this top Yukawa coupling and separate it from the modified contact interaction to gluon and photon. And the information here is that actually using this new observable, you get an individual or separate measurement of the top Yukawa coupling with a precision of the order of 10–20%, so something comparable to the TTH cross-section. And as I was mentioning, at the beginning of this talk, actually, if you want to perform with high accuracy this measurement of the boosted cross-section, then you better need to know with high accuracy the theoretical prediction for this cross-section. And as I was saying, actually, this is one of the processes which is known only at leading order in the standard model. So certainly here, there is a need from the theoretical community to go beyond leading order and include the next to leading order contribution to this process. Maybe it's actually something which is even more urgent than computing the n-cube halo contribution or correction to the inclusive cross-section, because there is more information again in these boosted cross-sections than the inclusive cross-section. And finally, another channel, I don't know how much time I have left, 5 minutes, okay. Another channel that I wanted to comment is the production of a Higgs boson off-shell, something that has been recently measured by the experimentalists. Again, due to the small value of the Higgs width, you will have expected actually this cross-section to be very small, but actually as a matter of fact, due to the particular enhancement of the coupling of the Higgs to the longitudinal polarization of the W and the Z, again, something that has to do with unitarity. This cross-section is actually rather important, and about 15% of the Higgs events are actually produced off-shell with an invariant mass for the 4 leptons, which are about 2 or 3 times larger than the mass of the Higgs. So certainly probing some high energy regime of the Higgs coupling. So what is also the reason of this enhancement here of the off-shell cross-section is simply that actually there is some interference between those two types of diagrams, the one diagram that involves the Higgs and the background that doesn't involve the Higgs. And each of those diagrams separately grows with the energy, and because of the unitarity properties of the Higgs coupling, actually there is a cancellation between those two diagrams. Which also means that, if you modify the Higgs coupling, then this cancellation doesn't occur anymore, and then you will have a huge enhancement of the cross-section. So this makes this channel actually a very interesting channel to probe any deviation of the Higgs coupling, simply because those deviations will be enhanced with the energy. And that's actually not what was done by the experimentalists or also few theorists. Actually, they were trying to use this experimental data to put some bound on the Higgs width, simply by comparing the off-shell production with on-shell production, where you get some sensitivity on the Higgs width. But again, to do this analysis, you need to make assumption. For instance, one big assumption that was made is that the coupling of the Higgs remains the same when you increase the energy, which is something which is not guaranteed at all. And as I was telling you, you actually want to use this channel to probe the evolution of the coupling with the energy. And actually this channel is also particularly interesting to disentangle the top loop from the contact interaction to the gluon, because energy dependence of those two processes are totally different. For instance, here the top loop contribution will have only a logarithmic dependence on the energy, while the contact interaction has more derivative, and then the energy dependence will increase. So there is really a lot of advantages to look at the off-shell production to disentangle these two effects, just using the different energy behavior. And that's an analysis that we have done here. Use this off-shell experimental data to disentangle again, or to break the degeneracy between the top Yukawa coupling from contact interaction to gluon and photon. And again, this is something, sensitivity of the order of 20%, so that will bring additional and competitive information compared to the TTH channel. Okay, I was planning to discuss multi-X channel, but I think I'm really running out of time. So you can look at the slide if you want at some point, ask me some question. And maybe I can jump directly to the conclusion. And the conclusion is actually what can we learn about new physics using X data. So certainly there is, you can think of the standard model sector, which is coupled to the new physics sector, with some particular mass scale, with a typical coupling G star, and G star will also be the coupling of the X to this new physics sector, in such a way that there is actually, by mixing, there is some interaction between the new physics sector and the standard model sector, which is controlled by coupling, which is the ratio of the standard model's coupling square divided by G star. So the question is whether actually it's better to search for new physics directly by looking at these new particles that can be heavy, or whether it's easier actually to look at deviation in the X coupling, and the deviation of the X coupling will be parameterized or controlled by this parameter psi, which is simply the ratio of the width scale square divided by the typical scale of this new physics sector F, the equivalent of F pi of QCD. While clearly the typical mass of this new particle will be G star, the typical coupling, times F. Right? So which one is the best, right? Either should we improve the direct mass search or improve the measurement of the X coupling? And actually the two things are related to each other for given value of G star, the typical coupling of the strong sector. Because for given value of G star, then you have a relation between the mass of the physics and the typical scale of the deviation in the X coupling. So if you think about high luminosity LHE, where the X coupling will be measured with an accuracy of the order of 5%, for weakly coupled models with G star of the order 2, you will have a comparable effect to the mass reach of the order of 2 TeV. But if the sector is very strongly coupled, then you will have a mass reach of the order of 15 TeV or so. And at a linear collider, or TLEP, this big 100 kilometer E plus E minus machine, then the sensitivity will be bringing down to 1%. So this means that you will really push the mass scale to very large value. So I need to stop here. So just telling you that there is a nice complementarity between direct search and precision X physics. And you can also compare with the direct search that will be performed as this 100 TeV machine. So this time 100 kilometer collider at an energy of 100 TeV. And this is the direct search for the resonances that people have estimated. And you can see that there is a nice complementarity between X physics and this direct search for new physics. Okay, thanks a lot.
Thank you, Professor, for the nice insights into X physics. We have time for a few questions. Questions? Any questions?
No question.
So you skipped over the multiple X processes. I guess I have a very general question. I mean, you know that the prospects for double X production are not great. It's going to be difficult to measure. For example, triple Piso coupling with any great accuracy anytime soon. what are the prospects for indirect measurements of strain electron?
There are some studies, for instance, in modified X-self interaction can enter at the loop level into single X processes, like for instance ZH. And people have tried to estimate the sensitivity that you can extract on the X-self interaction via ZH measurement, particular TLAB. As you know, TLAB can measure these things below 1 per mil, and then you get some sensitivity that is certainly comparable to what you can see directly at the LHC at high luminosity, even better probably. Now the question, is how many parameters should you include in your analysis? Even when people at the LHC have estimated the sensitivity even in the X-self coupling, they were only modifying the X-self coupling. While in gluon fusion, for instance, double X production by gluon fusion, there is certainly more than this X-self coupling. So there is many new parameters, many new couplings like TTHH that doesn't exist in the standard model, and this has also a huge effect in this cross-section. So this means that if you want to extract this X-self interaction, you also need to take into account some possible new coupling like that. So I think even the sensitivity at the LHC that have been estimated, I think they have been over-optimistic because of this effect. Right? That there is, again, some degeneracy that you cannot measure separately the two things, and you need to combine several channels to do that. So, yeah. At the end, I have a plot like here that shows you actually what kind of information you can extract from gluon fusion to double X production. And here is the self-interaction of the X, and here is a new coupling to two top quark. Right? And you see that actually, just by looking at the scale, that it's easier actually to measure this new interaction than measuring the X-self interaction. But again, this has to be done more properly using this description in terms of effective field theory.
One more question? Okay, if not, let us thank Professor Juan again. And for the last session of this morning, let me call to Professor Juan SANABRIA from Universidad de los Andes, Bogotá. He's going to talk about the LHC results for the Higgs.
So I guess I'll start. I must confess that I was very afraid to talk after Professor Ellis and Professor Grosjean, but actually it turned out to be really good because they covered all the difficult topics I was very afraid to cover, so I'll stick to the numbers and that will be much simpler. Okay, so I am presenting the results of the Higgs physics in the first round of the LHC on behalf of the ATLAS and CMS collaboration. So I have lots of results to present, so I apologize because I am going to be very quick. I hope I will be able. Well, the content of my talk, I will first discuss the main production and decay channels that led to the discovery of the Higgs, and also what have provided us with accurate information on some of those channels in order to measure in the best possible way mass, width, cross-section, spin, parity, all these couplings. I will move into other studies that are important, that was mentioned by the previous speakers: rare decay, stop-Yukawa coupling, differential cross-sections. And then I will talk about the physics beyond the standard model that we can hope to see through the Higgs sector of the standard model, now that we do have a Higgs sector in the standard model. And finally, I will briefly mention some perspective about what should we expect in the second round of the LHC and conclude. So, okay, as always, a little memory. These kind of things don't happen every day. Actually, I was that day at CERN, but I was not in the auditorium, not important enough, or didn't wake up like our student Luisa at 2 in the morning in order to classify over there. But it's a nice memory, and it was a great day, and these two gentlemen here were dressed for the occasion, as you can see. And their sense of elegance improved a year later when they received their Nobel Prize. And the ATLAS and CMS CERN and the LHC were mentioned explicitly on the announcement, so everybody in the experimental side got the credit. So the idea is, after all this, what have we learned about this particle during the last 2-3 years? So first thing we must mention is that this discovery and these studies were performed at the LHC, this proton-proton collider, that during the first round collided protons at center of mass energies of initially 7 and later 8 TeV. Here is ATLAS and here is CMS. ALICE and LHCb are the other two experiments. So during the first run of the LHC, the performance of the machine after some accident that we want to forget, first it ran at 7 TeV and later at 8 TeV, and especially at 8 TeV, the performance of the machine and the performance of the two experiments, ATLAS and CMS, recording all that excellent data, was exceptional. At 8 TeV, on the order of 20 inverse femtobars of useful data was recorded both by ATLAS and CMS. Here are the two detectors. I don't have the time to go into details. Some of you belong to these collaborations and have seen these kind of presentations 1,000 times. The other ones, I guess, also. So just to mention that they are, both detectors, and we will see from the slides, have very similar power in order to measure the physics for Higgs discovery and for search of physics beyond the standard model as well as standard model. Of course, there are differences in magnetic fields and here and there, but otherwise the two experiments have performed at an excellent level. The main production channels in a machine like the LHC, in a hadron collider, for the production of Higgs, we have gluon-gluon fusion, we have vector boson fusion, we have production in association with the vector boson, and we have the production of the Higgs in association with the TT bar pair. Those are the main channels, and we can see, as it has been mentioned already several times this morning, that the gluon-gluon fusion production channel is the dominant one, by far. Decay channels, due to the feature of the Higgs coupling to the other particles proportional to their masses, then, well, the top is not here because it's heavier, but otherwise we have bottom, W, Z, tau, and here we have these composite couplings that gives smaller branching ratios. So that takes us to what has been called the main 5 decay channels. Gamma gamma for Higgs going into ZZ star going into 4 leptons, the Higgs going into WW star going into leptons and neutrinos, the Higgs going into taus and into B and B bar. And here are the actual numbers for the branching ratios. One can see that 58% is dominated by BB bar. However, I have put it here last because of all the experimental difficulties with this channel. And the gamma gamma, even though has a small branching fraction due to the nice features, experimental nice features, first or second, these two channels are the ones that give us the best information. In order to put some order to the search for the Higgs and the properties of the particle, one could just make this kind of chart. In these columns we have the main production mechanisms, gluon-gluon fusion, vector boson fusion, in association with the vector boson and TT bar pair. And in these files we have the main decay channels. So here the red checkers would mean that work has been done and has been published, even if the statistics is not good enough so that the result is not that conclusive. The little hands here mean that work is in progress and should be published soon. Someone was mentioning the CC bar. Here it is empty. This box here is empty because the background is very difficult to handle, etc. So this gives us a view, or panoramic view of what has been the effort of ATLAS and CMS in order to move on with this kind of physics with the Higgs sector. We see a lot of red checkers, so the work has been done, the homework has been done, and I think the class will be approved. Okay, well, let's move to quickly mention what have been measured for the gamma-gamma channel. We have here two event displays with a couple of photos that would make candidates for Higgs events in that channel. Yes, okay. Fine, so again, due to the fact that there is no direct coupling of the Higgs with the gamma, is through loops, that makes the branching ratio small. However, with the identification of two good quality photons, and ATLAS and CMS were designed to maximize that quality, one can have a very good separation of signal to background in invariant mass plots for the couple of gammas. We see here clearly these little bumps that once you subtract the background become some very clear signals that are accurate enough to give us detailed information about the state. Okay. And here, the numbers. I want to emphasize again that the numbers that appear here for mass and strength are for this particular channel. Later, I will present results for combination of different channels that give us these values for both ATLAS and CMS. So there will be values that supersede these ones. So, but for this channel, the mass was 125.98 in the case of ATLAS and 124.70 in the case of CMS. And the strength of the signal, which I remind you is defined as the actual cross-section, let's call it, that was measured divided by the expected cross-section from the standard model, gave a value of 1.17 in the case of ATLAS and 1.14 in the case of CMS. Let's move to the other channel, which is CC going into 4 leptons. What's C star? Here we have prospective event displays. This one would have 4 muons, and this one has 2 electrons and 2 muons. For the 4 leptons, product of the decay of the Z. So here, this plot summarizes the search. Here is the invariant mass plot for the 4 leptons in the case of ATLAS and CMS. The first peak would correspond to the production of a single Z, and the second Z is radiated off shell from the product of the decay of the first one, so one has actually a single peak here. And this would be the signal. And as we see, there is a clear separation between the background and the signal. This channel is also very important since the measurement of electrons and muons is very precise in these detectors. Therefore, one has very accurate information of the final state that allows for extraction of values with high accuracy like mass, cross-section, width, parity. So together with the gamma-gamma channel, these are the 2 important channels when it comes to get those results. Then, again, partial results for this particular channel. For ATLAS, we have 124.51, for CMS 125.6, so they fluctuate here and there when you look at the whole picture, but around some value. And in the case of the strength, we have 1.44 for the case of ATLAS and 0.93 in the case of CMS, but with the uncertainties continue to be consistent with each other and also consistent with the expectations of the standard model with reasonable significance. Fine. The next channel is the WW going into leptons and neutrinos. The presence of neutrinos makes things harder, so this channel has lower sensitivity. So here the idea is not to identify a peak on some invariant mass plot, but to assume the existence of, knowing that there is Higgs, and here are the values of the masses used by each experiment for this analysis. Try to look carefully at the data to study very correctly in the best possible way the background, meaning the standard model signal without Higgs and with the Higgs, and do complex boosted decision tree analysis and likelihood fits, etc., to see an excess in the data that would point to the expected excess coming from states like this one. So the strength obtained by ATLAS 1.08 and by CMS 0.72 for this channel. with a significance a bit smaller than the ones that were obtained for the previous channels that are more sensitive, of course. Okay, so here we have event displays for Higgs going into tau tau. Similar situation. The taus, even those are leptons, are harder to reconstruct because they quickly decay, and then in the leptonic case you have these neutrinos, which then complicate the study of the final state. And in the hadronic case, well, you have to reconstruct jet-like taus, and that also has a lot of complications. So for the tau pair, we have these three combinations of possibilities, and many more other categories that come from the different, from if the reconstruction was in a given part of the detector or in another one, etc. So these analyses are very hard, but follow the same philosophy of the previous one. And here we see all these categories that were analyzed by ATLAS and by CMS in order to search for this signal in as complete way as possible. The strength of the signal, so here there is no value for the mass because again, you take the mass measure from gamma gamma for leptons or a combination or some value, and with that you can extract an excess of signal of a background that will give you a measure of the strength. And here we have 1.42 for ATLAS and 0.78 for CMS. BB channel is pretty similar. Let's see. Okay. That's what I mean. Yes. The BB channel, BB bar channel. Again, in the case of gluon fusion production channel, it would be confused with all the jets that accompany that event. So in order to kill all the background, one must try to tag that Higgs, for example, with the presence of a vector boson, like the Feynman diagram here shows, and then do a similar kind of study in which you try to search for an excess signal over the background after very careful studies of background, both with data and Monte Carlo. I just want to mention that I have tried to include the references for all these plots, so if you want to look into the details of any of these analyses, then you are welcome to consult all these references. So here are the results for the BB bar channel that has very not so good sensitivity. Mu equals 0.51 in the case of ATLAS and 1.0 in the case of CMS, with the significances that you see. Well, that was a very quick presentation of the the analysis associated with the main 5 decay channels. Now, with all that and more information from other channels, one can attempt to make measurements of mass as accurate as possible with cross-sections, spin and parity of the state, couplings, etc. So let's try also quickly to see what have been achieved by both experiments regarding these numbers. So the mass measurement comes from these two channels, gamma gamma, and these start going into 4 leptons. Combined likelihood feeds to the data. Those 2 sets of data were performed by ATLAS and CMS. And the result, Professor Ellis this morning discussed in detail these feeds. The results are ATLAS 1.25.36 and CMS 1.25.03. So as this is giving us also some lecture on statistics. As you combine more and more data, then things start to merge. There should be a combination of the results from ATLAS and CMS within weeks before the end of the year, we hope. Now, another topic that Professor Brojan saved my day by explaining all these complicated things. So, the expected value of the width of the Higgs in the standard model is on the order of 4 MeVs. These machines operate at TeVs, and have granularities on the order of GeV, so measuring something of the order of MEVs was not easy. So I think I passed this one. So here is a little bit of what was explained in the previous lecture. The idea of using the Higgs going to ZZ channel and looking on shell and off shell at this channel and profiting from the interference between these kind of processes leading order in order to obtain a measurement of upper value for the width that is in the same order of magnitude of the expected value for the standard model. So was already explained, then I move quickly to the results. The problems also mentioned come with the lack of accurate calculations at higher order for the background in the off-shell region. Then ATLAS resorted to move these parameters that parameterizes the lack of knowledge on that background between a value of 0.5 and 2.0, and that's why the upper value quoted by the experiment is within a range. While CMS used another kind of approximation that allows them to fix the value and treat the uncertainty on this procedure as a systematic, quoting a value of 22 MeVs, while ATLAS gives a value that ranges between 19.5 and 31.3 MeVs. This is a nice result because it was unlikely that these experiments were able to come out with results in the region of tens of MeVs given the range of energies that are handled. So, and also it's showing us that the width of the Higgs is not grossly different from what one would expect from the standard model. Signal strength. Here then we take all the channels that have been measured and all the strengths that have been measured and combine them, and then ATLAS reported initially a value of 1.30 and CMS, as mentioned also this morning, out of a coincidence comes out with a result that is actually 1.00. This plot, it must be emphasized that this plot that I'm showing here from ATLAS has all dimension channel results, but new results have been obtained, and actually those are the ones that I presented in the previous transparencies. So a new combination fit comes soon, but ATLAS recently published a updated plot for each of the channels, but still the combination, the updated value on the combination is not there. Also mentioned this morning, the new updated values for these channels have moved closer to 1, so one would expect that the combination value from ATLAS would move down from 1.30. Again, things start to converge when you start piling up data. Speed and parity. The idea would be to be able to, through angular distribution, for example, make a direct measurement of the spin and parity of the state, but with the kind of data we have now, that's not a possibility. So the approach was to construct kinematical discriminants for hypothetical particles with different values of spin and parity, and compare them with the data to see which one comes favored. So as it turned out, and you already know, spin equals 0 and parity equals plus, which means a scalar state, was highly favored. And the other possibilities taken into account by ATLAS, for example, looking at Higgs going to gamma gamma, or Higgs going to ZZ or WW, pseudoscalar, vector boson, and graviton-like states were rejected at very high confidence levels. Similar rejections were obtained by CMS looking at the ZZ and the gamma-gamma channel separately. And so by looking at all these results, what one concludes is that the hypothesis of a 0 plus state comes highly favored, and you just can't say that is pretty much it at this level. Fine. Couplings. Again, this was also a hard transparency to explain, but it's already been explained and there were no questions, so fine. The idea of the Higgs coupling to the different states of the standard model in a different way because of its proportionality to the mass makes the landscape of the couplings complex to analyze. Then both ATLAS+CMS have defined these kappa factors that will measure deviations from the expectation of the standard model at the production and decay channels. And also some, within this framework of kappa deviations from couplings, that sometimes people refer as couplings, some benchmarks in order to investigate the nature of those deviations in relation with particular features of the physics that should be behind it. Here, this proving custodial symmetry should be in quotations, okay? But then you can group those couplings in different sets. For example, just a single deviation to measure the amount of deviation of the couplings measured with respect to expectations from the standard model, or group the vector boson couplings and the fermion couplings, probing the fermion sector, the up and down families of the fermions, try to see what is going on with the composed couplings, gluon and gamma, for example. The relevance of all these was mentioned in the previous lecture in great detail. Minimal parametrization, like main families of couplings, and all this allows you to investigate different features of the landscape of couplings of the Higgses. Some of those couplings, especially those loop induced, would be functions of the other couplings, and these functions would have to be calculated. And the reference of this comes from the LHC Higgs cross-section working group. The idea, as also mentioned before, is to move for next run from these to effective field theory calculation that will give us a more fair assessment of the Higgs coupling structure. Okay. Here are some examples, also shown in previous transparencies of the searches done, of the studies done in these two publications by ATLAS+CMS of the coupling structures, and how within the uncertainties of those studies, and here this is only one plot as an example of CMS, and another plot as an example of the work done by ATLAS, but in the publication there is all kinds of plots and all kinds of fits, investigating all the benchmarks that I mentioned previously. But the conclusion, as also mentioned this morning, is that the Higgs boson couplings are in good agreement with the standard model Higgs boson hypothesis, no strong deviations. And that would summarize that the plot that has been discussed in both talks. That would then tell you that this has, it quacks, so it does behave like a Higgs. Details here, details there, but it does play that role. Other studies, rare decays, Higgs going to mu, Higgs going to C gamma, Higgs going into two gammas, but one of them is virtual and radiates off a pair of leptons. Yukawa couplings, and the measurement of the first measurements of differential cross sections. Just a little propaganda. This channel I won't present here. In the case of leptons being muons, it will be presented by our student this afternoon. Her PhD thesis is on this particular channel. Fine, let's see. Z gamma. So has a small branching ratio, so the quality of the results is not as previous results that I have presented. ATLAS puts an upper limit for the for the 11 times the confidence level is an upper limit for the branching ratio, guys. Which means that any model that predicts, and there were models that predicted for these particular channels values more than one order of magnitude larger than the standard model expectations would be ruled out. So these results have some meaning in order to rule out some theoretical predictions. CMS presents a result in which the upper limit ranges between 4 and 25 times the standard model expectation. Similar situation with the Higgs going to mu mu. It has a very weak signal, so the upper limit in the case of the ATLAS result is 7 times the standard model expectation, and the limit presented by CMS is 7.4 times. Higgs to top Yukawa couplings, again it was discussed in great detail in the 2 previous talks, the important role that the coupling of the Higgs to the top play in all this physics and in possible physics beyond the standard model. So here are diagrams that let you see. Here are the main production channels, here are the one of the important decay channels, and in one of the important production channels also, and the possibility of the top radiating off a Higgs here. So ATLAS has searched for Higgs boson association with top quarks, looking at the gamma-gamma decay channel, and have put these limits on the value of the kappa parameter for the coupling of the top to the Higgs that ranges between -1.3 and 8.0. It's not that precise, but as it was mentioned in previous talks, it's very hard to measure. So here we have results from CMS. CMS looks at the Higgs in the hadron, photon, and lepton channels, and comes up with a value for the strength of the signal that is 2.8 plus or minus 1.0, which is compatible with the standard model at 2 sigma level. That's one way to put it. Someone else could call it a fluctuation. Fiducial cross-sections have been published by ATLAS, not by CMS. Here the word fiducial means that the cross-sections are integrated over the effective volume of the detector. So it means that to do a fair comparison with theory, the theoretical calculations have to be integrated over the same phase space. This way you don't have to do assumptions or extrapolations in the regions of phase space that are not directly covered by the detector, and then this can be a very fair way to compare theory and experiment. Here is important to point, here in this column we have differential cross-sections with respect to the transverse momentum of the Higgs boson, and here we have total fiducial cross-sections as a function of the number of jets that accompany the signal. And the thing to notice here is that even though the shape of the result is the same, there is an overall shift up in the result for this differential cross-section coming from gamma-gamma. But it is within the uncertainties in statistical agreement with the standard model expectations given these kind of calculations. Okay. Higgs and BSM, neutral and charged Higgses, invisible decays, flavor violations, all those topics mentioned in previous talks. The search for minimal supersymmetric standard model neutral Higgses. The simplest scenario is the 2 Higgs doublet models. The minimal supersymmetric standard model could be seen as that, but it's not only that because it has the rest of the supersymmetric state, so it restricts the degrees of freedom of the Higgs sector. But in those cases, what we should expect to see is 2 scalar Higgses, a pseudo-scalar Higgs, and 2 charged Higgses. In this kind of studies, it is often assumed that the 125 GeV Higgs that was observed would correspond to the lightest one. But therefore, one should look for the heavier one, which is the scalar and pseudo-scalar. But it could also be that the one that was discovered was this one, and then one should search for lighter ones. So the experiment should try to cover as much of the parameter space in terms of mass. So let's call all these possibilities phi, and then let's look at the experimental results for those searches. In the case of tau tau, this hypothetical neutral Higgs decaying into tau tau, the searches from ATLAS have gone from 200 GeV roughly up to 1 TeV, and no significant excess has been observed on the data that points to the existence of these states in that range. Similar situation for CMS that have searched in the range from about 100 GeV or a little bit lower up to 1 TeV, and again no significant signal or excess is observed in all that range related with the existence of these states. Other kinds of resonances. Look for resonances in the gamma-gamma or in the WW and ZZ channels have been performed by ATLAS, scanning the range between 65 and 600 GeVs, CMS 150 to 850 GeV. In the case of the WW and ZZ, we have this range covered by ATLAS 260 to 642. And CMS between 145 and 710, and also the possibility of heavy Higgs decaying into two Higgses or this other one, the pseudo-scalar decaying. But as you know, no significant deviations from standard model expectations, no signal, clear signal observed. Charged Higgses. So here are some production and decay channels of these kind of Higgses. So ATLAS performed searches in the Higgs going into tau nu neutrino, and Higgs going into CS bar. ATLAS Higgs going into TB, tau nu, and CS bar, and again, no significant deviation from standard model expectations have been observed. Higgs to invisible decays. So this channel has is very relevant in its possible connection with the search for dark matter. In particular, in those models in which the interaction between the dark matter and ordinary matter is mediated by the Higgs, like the so-called Higgs portal dark matter models. Experimentally, it's quite challenging because it is invisible, so you have to try to see it somehow. And one way to see is to target with the presence of a vector boson, and knowing that there is a Higgs of 125 GeV, then analyze carefully the data to look for the kinematical signature of the presence of this kind of process. In the case of ATLAS, the upper limit to the branching ratio for that kind of decays is 75%. In the ordinary standard model, the invisible decay comes from Higgs going to ZZ that goes into neutrinos, and that has a small branching fraction on the order of 0.12%, if I am not wrong. So if you were to see some signature in there, it would definitely point towards something beyond the standard model. So these limits are not very strong. However, they do impose, as I'll mention later, some constraints on these models in which the interaction between dark matter and ordinary matter are mediated by the Higgs. And actually, the upper limits for the cross sections come stronger than the ones coming from direct searches, but of course within that hypothesis. Here is the case of CMS. CMS used the Higgs, tagged the Higgs with the vector boson, but also in vector boson fusion channels, and came out with a 58% upper limit for the branching ratio of the decay of the Higgs into invisible. This ATLAS and CMS results then can be turned into upper limits for dark matter interaction cross sections that go beyond what has been measured by the direct searches, but is model dependent. Flavor changing neutral currents have been searched in the decay of top quarks to other quarks accompanied by Higgses by ATLAS and CMS. Why all this is interesting and important was already discussed in detail in previous talks. So I just report these upper values for the branching ratio, 0.79% in the case of the result of ATLAS and 0.56% in the case of CMS. So no significant signature of flavor changing neutral currents in these branches. Lepton flavor violations. Again, discussed this morning. The experimental data existing restricts a lot the possible lepton flavor violations that would connect electrons to muons through the careful study over the years of muon decay. However, in the case of the tau, that's not the case. The experimental constraints are not that great. So there is a hope to search for this kind of violations in channels like mu going to tau, and here leptonic and hadronic taus. CMS have done these studies and have observed a slight excess on the signal on the order of 2.5 sigmas. So if one would interpret this as a statistical fluctuation, it would set an upper limit for the branching ratio of this kind of decays of 1.57, when the expected limit was 0.75. So here we have that factor. And if it is interpreted as an actual signal, then it would give a branching ratio of 0.89. And that is the panorama of what the Higgs physics was at the LHC Run 1 by ATLAS and CMS. Very soon, in the spring of 2015, the LHC will start its second run. That means the first run and the analysis related with the data of the first run will come to an end soon. So the big picture of what has been the Higgs physics, I guess, won't be much different to what I have presented to you today. As I mentioned, in the spring it will start running, and it should be running until 2017. Initially, it should run at 13 TeV in the center of mass of the collisions. The idea would be, if everything goes well, to increase it up to 14 TeV. The bunch crossing, the time between bunch crossings should be the highest possible, 25 nanoseconds. Understand initially, just to go into the safe side, it would be at 15 nanoseconds, but it should quickly move to this value. It's very important to achieve these instantaneous luminosity goals, 10 to the 34. Integrated luminosities on the order of 40 inverse femtobarns. Must remember that in the ATV run, it was, the data recorded was 20 inverse femtobarns. So it would double the luminosity per year. And over 3 years, it should go beyond 100 inverse femtobarns. And that means roughly a factor of 5 in luminosity, and roughly a factor of 2 to 3 in cross sections, in Higgs cross sections, when you move from 8 to 13 TeV. So it gives us 1 order of magnitude in terms of statistics. So here it is, 1 order of magnitude more events for precision measurements, observation of rare decays, and search for new physics. The precision measurements, important precision measurements for mass, for the main production and decay channels. Try to take these decay channels to a 5 sigma level. Try to study the coupling structure of the Higgs at a much more detail than it was done in the first run. perhaps even get into a denser structure by measuring angular distributions, using an effective field theory approach for the couplings, measuring carefully differential cross-sections for those channels that allow it, improving measurements like Higgs going to muons, resonant and non-resonant searches for Higgs pair production, CP violation discussed in detail in the previous talk, extended limits in a series of new decays and invisible decays, extended limits on searches for new Higgses, etc. Summary. This plot and the similar plot from CMS just show us the level of achievement of the LHC and the experiments. The mapping of the standard model at 7 and 8 TeV is just impressive. And in these charts, new entries have been added related with Higgs cross-sections. Here we have gluon-gluon fusion, production cross-section, and vector boson fusion. Similar results for CMS, a bit more detailed chart, this one. And we have here this disagreement mentioned also this morning, but not disagreement, this fluctuation. Fine. So the results of this first run are impressive, especially in the Higgs sector. The standard model has been consolidated at an impressive level. The Higgs boson has been discovered. Measurements with sensitivities of 5 sigma or more for gamma gamma, leptons, 4 sigma for tau, 2 sigma for BB bar, for the combined result of the determination of spin and parity, also a very high sensitivity. Initial measurement and good accuracy of couplings. But again, no solid evidence of any new physics in the Higgs sector, even though there are some intriguing results. Perhaps no. So, I truly was going to mention that one not just thank all the ATLAS and CMS collaborations for these results, but also LHC staff, CERN staff, and more than anything, all the theories that seldom get their credit for these kind of achievements, for all the calculations, all the Monte Carlos, all the ideas, all the explanations, all the support, that allowed a large community of people from all over the world to be able to work together and get this kind of results. So that to me is the most impressive thing of all this, that so many people of so many cultures get together and without a clear hierarchy structure manage to do this. So I invite you to consult these 2 pages, the ATLAS Higgs public results and the CMS Higgs public results, where all the public plots that I have presented today, all the results and new results that are coming out every day will be available. I don't know if you noticed, but in the references that I presented here, a large fraction of them are from the last 2-3 months. So results are coming out as one presents the talks. And actually during the preparation of this talk, I had to change transparency because new results had come out. So that puts an end to my talk. I thank you very much for your attention.
Okay, thank you very much, Professor SANABRIA, for a very neat and quick talk. We have time for questions.
Can you comment on the expected sensitivity at RUTA for the Higgs width, the total width of the Higgs boson?
The measurement of the upper limit for the Higgs width?
No, yes, for RUTA.
Honestly, I mean that analysis is so complex that I wouldn't have a guess, and I don't know the answer to that one, but maybe someone does. No.
And also you showed for CMS the results of Higgs to mutable. What about ATLAS?
For that channel, Atlas has not published yet. These results are very recent, and the Atlas results should be coming.
So for the determination of the bottom Yukawa, it would be very useful to have some data on H2BB power in gluon-gluon fusion or vector boson fusion even. Is there any chance, or is it completely unrealistic?
You BB bar in which production channel?
So I know we have it in associated production and TT bar, but to determine the tau bottom Yukawa, it'd be very useful to have it in either gluon-gluon fusion or vector boson fusion. Is it possible or not?
In gluon-gluon fusion, the background is very hard, and the fact that that box is still empty, I don't think it will be filled out before the next run starts. For the other one, I am not so sure. I don't see why it will be done.
So just a quick comment on that is that I believe for vector boson fusion, the cross sections will be extremely small, even though the backgrounds will be smaller, so still will be hard to see to do that measurement because cross section will be extremely small, background will be small, but still you're killed by the cross section, so it will be hard to measure. I will get that.
Any other question, comment? Okay.
So can you comment with more detail about this measurement of the Higgs CT bar power coupling from associated Higgs bar product?
I don't have the transparency. I have to see if I'm able, because here I presented like 30 analyses, and I have not been involved on that one, so maybe I would advise you to look at the note, because I guess that I won't be able to do any intelligent.
Okay, last question. Okay, if not, let us thank Professor. We are going to have lunch together. We will walk till the end of this block in this direction. And at the corner there is a building, and the lunch is going to be in the second floor of that building. This direction till the end of the block.
And it's not just time when I have the outline. So the most natural way to make interface between soft and hard interaction is factorization theorems, which tells us that large distances soft interaction factorize from hard collision, and moreover this factorization, this soft part is universal, and once you measure it in one hard process, you can predict another hard process. So this is, I would say, is a partial solution of the problem. However, it has more problems. For instance, if you want to predict something new, we perform measurements in deep enlace scattering and want to predict not inclusive but exclusive or semi-inclusive reaction. It's impossible. You have to introduce new functions and make new fits to data. So it's not very successful phenomenology, and for this reason I switched to alternative description, the dipole description, which became extremely popular over the last decade or two. And it has many advantages, also disadvantages. It can predict, for instance, diffraction, which is impossible in standard factorization-based pattern model. Nowadays we have mostly high energy and small x physics, so it's pretty effective phenomenology. And then I will discuss in more details diffraction. We'll demonstrate that factorization, which is used by many people for diffraction, fails. It's not correct. And I will demonstrate on several examples with radiation of abelian particles like de gauge bosons, Higgs. Then I will discuss specific features of diffractive gluon radiation, and eventually we'll switch to gluon shadowing, to nuclear shadowing, which is tightly connected to the physics of diffraction. So let me briefly remind what is the collinear factorization. If we have a hard reaction, and this is a classical example of hard reaction, deep elastic scattering, the soft interaction controlled by the proton structure factorizes from the hard process of absorption of the highly virtual photon by a quark, and this soft part can be expressed via a structure function F2, which is just sum over quark distributions, and quarks and antiquarks are distributed in the proton over the fractional light cone momentum x, and it depends only on q squared. And at the early years of the pattern model, it was found that such a structure function depends only on x and is q squared independent. And this actually would be true if the number of partons were a conserved number. However, partons are not classical particles. They are quantum fluctuations. So when you make a Lorentz boost, for instance, you can increase or decrease number of these partons, like in QED, equivalent photons. And also, the number of partons which you can see depends on your resolution. So when you increase the photon virtuality, you increase your resolution, and you see more and more particles, partons inside the proton. So the number which you can see at a given scale is fixed by your resolution, but when you increase, you can look inside the partons which you have seen already and see more partons inside it. So when you increase resolution, you increase number of partons, and they are produced by partons at smaller resolution. So this is a sharing process. When the momentum of partons is splitting process, momentum of partons is shared between several new partons. This means that partons at large X fit down and increase population of small X region. However, the number of partons at large X is reduced, and this means the following simple prediction: when you increase Q, then at large X, the parton density should fall down, and small x it should rise. And data perfectly confirm this expectation. Moreover, the curves plotted here are DGLAP evolution, which describes Q squared evolution, DGLAP evolution equations, and a couple of examples for quarks and gluons is shown here. So it shows how the parton density changes with variation of the saturation scale. And structure functions are usually fitted to data in global analysis of data for deep inelastic scattering. And the typical strategy is like this. We cannot calculate the structure function, this for sure. And this is because of the unavoidable admixture of soft interactions, which we do not know. However, once you know the structure function at a given scale, you can increase your scale a little bit, and variation can be calculated perturbatively. So we cannot calculate F2, but we can predict how it changes with at high scale, increasing scale. And this is very important because otherwise we would not be able to fit data. Data for F2 are usually scattered over x and q squared, and for each point you need a new function. You have to fit many experimental points with many different functions. However, having enhanced this theoretical tool, DGLAP equation, we can do it simultaneously for all points. And usual procedure looks like this. One makes a parameterization. I said it ad hoc. It's maybe not ad hoc, but at least education guess. You make some parameterization, introduce parameters at a some starting scale, which already brings uncertainty. You don't know where your perturbative population and factorization start working. So usually it's 1, 2 GV q squared starting scale, and then you can evolve this parameterized initial distribution up to any q squared and compare with many points at different q squared. And if you did not succeed, you should adjust initial distribution, change the parameters in a way that you eventually will describe all data at all x and q squared. And this is how it's done in the literature. So presently we have a pretty good knowledge of F2 as function of x and q squared. And another advantage of factorization theorem is universality, possibility to use the same parton density in other processes, and it's proven for Drell-Yan, and make predictions. So for Drell-Yan process is annihilation of QQ bar from colliding hadrons, which produce lepton pair, and it's very a good process for experimental detection, especially muons. And the cross-section can be expressed via this universal quark densities measured in deep inelastic scattering, times the hard cross-section, which is QQ bar going to dilepton, heavy dilepton, and the dilepton mass imposes the hard scale of this reaction. So since we know this quark density, we can make prediction, and it was a surprise in the early years of factorization that cross-section fails. It underpredicts the Derelian cross-section, underpredicts by so-called K factor, which is pretty large, about 2.3. And the reason why it happens intuitively pretty clear. It comes from the Sudakov suppression. For instance, if you have a plus or minus annihilation and you want to produce just two quarks, QQ bar, then it turns out to be pretty difficult, because in QED, when you have any abrupt variation, change of your electric current, you immediately produce radiation. For instance, in this case, when we produce in annihilation QQ bar, these quarks are produced without color field. They are bare quarks. They have to regenerate color field eventually, and regeneration becomes a radiation of gluons. So usually when we have electron positron collision, we produce at least two jets, and each jet is a quark radiating lots of gluons. However, it's possible to produce just QQ bar, but it is suppressed, and this suppression is called Sudakov suppression. So this K factor comes from this suppression. We wanted to produce this lepton pair without gluon radiation. And of course, it was understood immediately that the source of disagreement is high order corrections. So this is first order corrections next to leading order, and one has to include all possible radiation, including virtual gluons, and do the same in deep inelastic scattering, and then agreement is pretty good. Okay, now I want to switch to the alternative dipole description. And as I mentioned, the predictive power of this factorization scheme is quite restricted. For instance, in deep inelastic scattering at Hera, it was a big issue to measure diffractive scattering. And after you made all your feeds for inclusive deep inelastic scattering, can you predict diffraction? You cannot. You have to introduce new function, diffractive structure function, and make a new feed to diffractive data, which is possible, but it's not exciting business when you have to introduce every time new parameters and describe the data to be explained. And in this respect, this alternative description has some advantages. And first of all, I would like to notice that pattern model description is not Lorentz invariant. Lorentz invariant is only the observables. They must be the same independently on the reference frame. However, when you make a change of your reference frame, the whole pattern interpretation changes. And in this respect, I would say that F2 is proton structure. At small x is quite conventional statement. With the same, on the same footing, I could say it's not proton structure, it's photon structure. It depends on reference frame. For instance, if we produce a couple of C quarks as a fluctuation, who is the owner? Do they belong to the beam or to the target? It depends on the reference frame. Being in the rest frame of the target, all fluctuation is produced as a quantum fluctuation of the beam. So I should say this pair belongs to the beam. and vice versa, when I'm sitting in this reference frame, then this is the source of this fluctuation. So for this reason, I said F2 is not really structure of the proton. For valence quarks, it's okay, but not for C quarks at small x. And deep inelastic scattering in the rest frame of the proton looks differently. It looks like fluctuation. It's not absorption of the photon. It's fluctuation of the virtual photon to a QQ pair, which interacts with the target, with the proton. And then one can write a factorized expression, but for the cross-section. Cross-section is the same F2 up to kinematical coefficient. So F2 is just cross-section, and cross-section is cross-section of interaction of this photon with the target, which interacts not electromagnetically, it interacts developing a strong interacting fluctuation QQ bar. And there are different fluctuations. It could be QQ bar plus gluon, etc. So this is the lowest Fock component of the photon. And for this component, we can write that cross-section of the photon is given by the distribution, light cone distribution function of QQ bar in the photon times the cross-section of interaction of this QQ bar dipole with the target. It also depends on X, on Bjorken X. It's implicitly here. So the alpha, it's my notation which I will be using, is the fractional light cone momentum of the photon carried by one of the quarks, for instance, by quark. So they share the momentum of the photon in fractions alpha and 1 minus alpha. And this kind of factorization, in fact, is an assumption here, but later I will give some argument why it should work. Once we have this formula, we need to know the light cone distribution functions of quarks in the photon and the dipole cross-section. And the dipole cross-section, if you treat it perturbatively, it should be universal, flavor independent. You can use it in any hadronic or electromagnetic process wherever you have QQ bar dipole, and it could be heavy quarks or light quarks, or perturbatively there should be universality. Whether it's still true, including non-perturbative interaction, is beyond our knowledge, I would say. So what people usually assume that it still works, and this cross-section is universal. And so far, I don't know any serious trouble with this assumption. However, we should keep in mind that this is assumption. And this cross-section is well fitted. There is nowadays a lot of different parameterization and fits to Hera data for deep inelastic scattering at small x, and this formula actually gives you access to this cross-section, which is well fitted. There is a lot of interesting physics around. The next part of this factorized expression is the distribution function, which can be well calculated perturbatively. So it actually was done many years ago, first time by Bjorken and Kogut in the beginning of the 70s. And it depends on the polarization of the photon. For transversely and longitudinally polarized, they have different shapes. And since it comes from the quark propagator, it's not a surprise that we have here modified Bessel functions, K0, K1. And the argument of this Bessel function is epsilon times transverse dipole separation, where epsilon is shown here. So it is proportional to q squared, epsilon squared. However, times this factor, alpha 1 minus alpha fractional momenta, and this makes life quite interesting, because what one could expect naively, how to answer the question, what the typical size of this dipole. One should say if the photon has virtuality q, it should be 1 over q. However, this is not fully true, so mean size is 1 over epsilon. And in epsilon, you do have q squared here in epsilon squared. However, if you consider very asymmetric fluctuation, when almost the whole momentum is carried by quark or anti-quark, which means alpha is very small, or 1 minus alpha is very small. This smallness will compensate q squared, and then the size becomes or hadronic sizes, big size. It's no hardness anymore. So Bjorken called these configurations aligned jet configuration. This is standard terminology. So for such endpoint behavior, we have instead of hard process, we have soft contribution. However, these fluctuations have very small weight. It's very improbable. It has phase space for them is very small. It's 1 over q squared compared to 1 for symmetric configuration. And if for a moment forget about this aligned jet configuration, the typical size is indeed 1 over q squared. And according to color transparency, dipole of the size r interacts, if r is small, is roughly like r squared. And then you will get 1 over q squared behavior. So this is the origin of Bjorken scaling in this language. Now, let's try using this scheme. Let's try to predict Brillouin, similar to what has been done for inclusive reactions in the factorization-based scheme. So in this case, we have two Born graphs, radiation of the, first of all, the Brillouin process does not look anymore as Q-cube annihilation. In the rest frame of the target, it looks like Bremsstrahlung. So the projectile quark from the beam can radiate heavy photon, and this photon, heavy photon, or gauge boson, they decay to heavy dilepton. And this heavy photon can be radiated before or after interaction. And when you square this amplitude, then you notice that the impact parameter position of this quark before radiation and after radiation are different, because radiating a photon, the quark gets a transverse kick and changes impact parameter. So we have a different impact parameter in the final state compared to the initial state. When you square, you have Q from one amplitude, and complex conjugated amplitude has shifted impact parameter Q, so you get artificial dipole, QQ bar. In this process, you don't have real dipole like in deep elastic scattering, but artificial dipole. And with this artificial dipole, making assumption that cross-section, dipole cross-section is the same as measured in deep elastic scattering, we can, one can derive such a factorized formula which looks actually pretty much similar to what we had in deep elastic scattering. However, the light cone distribution function, which also can be calculated perturbatively, is a little bit different, not much. And the cross-section depends not on transverse separation, but fractional momentum alpha times transverse separation. Otherwise, it's the same simple, and it doesn't need high order corrections. Everything is included. And one, this is for quark scattering. For proton scattering, for PP, for instance, one can use this formula. use quark distribution function and this dipole formula. And this is just an example how it works in practice. It was done by Raiffeisen, Penck, and Nayak some years ago, and they compared next to leading order calculations, which is shown here by dashed line, I think the upper dashed line. And solid line shows dipole calculation. And dipole formalism is valid only at sufficiently small x. You cannot go with this formalism to large x. In fact, all fits done at Hera start below x.01. So in principle, these data of 772 experiment, they are not actually legitimate to be described by dipole cross-section, but these authors were brave enough to continue dipole description up to high x, and of course at large x it doesn't work, but at small x it goes just on top of the next to leading order calculation. And prediction for the energy of RIC, 500 square root of S 500 GeV, is just perfect. Below 0.01, you cannot see any difference between next to leading order calculation and this. But the difference is practical difference. Next to leading order calculation is extremely difficult business. You have to sum up lots of graphs, both in deep enlace scattering in trillion. But dipole formula is just back of the envelope type of calculation. One can do it with simplest calculator. So, and you see in practice, they give exactly the same. Okay, now I switch to diffraction, and I start with diffraction in deep enlace scattering, which was well measured at Hera. And it looks like, in inclusive reaction, this is photon plus proton producing X. So only electron is measured. However, if you produce final state proton, which you also measure, and don't measure what is produced here, you will have rapidity gap. And this diagram can be treated as excitation, diffractive excitation of the virtual photon. So virtual photon plus proton goes to proton plus X. And X is the excitation here. In terms of quarks and gluons, you can treat it like this. This is inclusive process where you have inelastic collision between photon and proton. Tautologically, it means color exchange with radiation of many gluons. And what is different for, and you produce QQ bar plus lots of gluons. What is different in diffraction, instead of this colored exchange, you have colorless exchange, what is called pomeron. And then you produce QQ bar, which decays to QQ bar and gluon, so this is what is called here X. So in both cases, you produce QQ bar, but here you produce two colored jets, and here you produce colorless system, jet system. And the dipole formalism allows you to predict this cross-section without any new fitted parameters. So it's for the forward diffractive cross-section, you have the same formula which we had for the inclusive cross-section, except the dipole cross-section must be squared. And here you have the same light cone distribution functions. So one can do straightforward calculations and compare with data, except, as I said, this is the lowest Fock component of the photon, only QQ bar. One should add also fog state of the photon, which is QQ bar plus gluon, then in the final state you produce not just QQ bar, but QQ bar plus gluon, and it was not included here. And in terms of Regge phenomenology, you can treat, for instance, these two possibilities with production of extra gluon and without gluon as so-called Pomeron-Pomeron Regge graph, and you have only excitation of the quark skeleton of this hadron, or diffractive radiation of gluon, then you have triple Pomeron coupling. So what is written here is only this is PPR term, and triple Pomeron term is needed if you want to include diffractive gluon radiation. Now I want to restrict myself with QQ bar for component, and I would like to look how much to F2 or to the photon-proton cross-section contribute soft and hard interaction. There is interesting interplay of soft and hard. Let's, as I said, a line jet configuration when QQ bar shares light cone momentum very asymmetric, in a very asymmetric way. Almost the whole momentum is taken by quark, and anti-quark has a small fraction. In this case, the fluctuation is soft. It has large transverse size, and I call such a line jet configuration soft. Otherwise, if this asymmetry does not compensate the scale Q squared, I call this hard. And first of all, I look at weight factor. And the weight, the probability to have hard symmetric fluctuation is about 1. So most of fluctuations are of this kind. And soft fluctuation, as I already mentioned, is very rare configurations which have probability 1 over Q squared. So this is much bigger. However, in the dipole formula, I have product of the weight factor times cross-section, and cross-section are also different. This hard, which has the size 1 over Q squared, it has cross-section 1 over Q squared. And soft is big, and it has hadronic size cross-section, roughly 1 over MQ squared. So this has large weight factor, small cross-section. And here it's vice versa. You have small weight factor and large cross-section. When you calculate product of them, they are of the same order, 1 over Q squared. And this is interesting observation, which means that one cannot say that deep enlace scattering is a hard process. It's 50-50. It's not literally 50, but they have finite contribution of hard and soft collisions, and just increasing Q squared, you cannot get rid of soft part. It remains about the same up to logarithmic corrections. So this is important to understand, and this you cannot understand in the Parton model. In this dipole description, it's pretty obvious. Moreover, when I look at diffractive cross-section, as I said on previous slides, that the formula is the same, except sigma must be replaced by sigma squared. And it changes. Instead, you have, for hard, you will get square of the cross-section. It's 1 over Q to the 4th. And for soft, only the weight was small, and the weight is the same, and the cross-section is large. And you have much bigger cross-section than that. And we have very important conclusion that diffraction, what is usually called hard diffraction, is not really hard, it's soft-dominated. Nevertheless, this diffractive F2, it was proven that it obeys the Glab evolution equation. It is soft-dominated, but there is small part of hard process, and when you evolve the scale, the variation of this hard part can be calculated with the globe evolution equations. So this is fine. However, in general, the cross-section, diffractive cross-section, is almost purely soft. And another observation from this simplified table, this was one of the first experimental observations at here, which surprised many people, that fraction of diffractional excitation relative to inclusive is practically Q-squared independent. And you can see it from here. So if you take this diffraction over inclusive, it's Q-squared independent. Okay, then it was a lot of activity about the hypothesis made by Engelmann and Schlein, which looked at the triple Rödge interpretation of diffractive process, which looks like this. You have diffraction via Pomeron exchange. So when you square this diffractive amplitude, you get this cross-section. And what you have here is virtual photon Pomeron scattering and inelastic interaction. And in deep inelastic scattering inclusive, we do the same with proton. So gamma star proton gives you the Parton distribution in the proton. And here, instead of proton, you have Pomeron target. So it might be exciting opportunity to measure Parton distribution in the Pomeron. Of course, one should understand that this is suddenly oversimplified because Pomeron is just a name. It's not a particle like a proton. It's quite complicated gluonic exchange, which we are still don't understanding sufficiently. However, it's kind of assumption which looks nice. And the idea was one can measure the Parton distribution, quarks and gluons inside the Pomeron, and then go to other reactions. For instance, hadronic diffraction at high energies. One can predict where we have also Pomeron exchange, assuming it's universal Pomeron. You will get prediction for diffractive hadronic reactions. And this has been done using H1 analysis for the Pomeron structure function, and this prediction for large PT dijet production, diffractive dijet production, and this is what was measured by CDF experiment, and you see an order of magnitude difference. So this was disappointed. Nevertheless, it was pretty quickly understood how to explain it. In deep inelastic scattering, we don't have so-called absorptive corrections. So because deep inelastic scattering is in a sense elastic scattering. You have QQ bar fluctuation as the initial state and QQ bar in the final, so it's elastic. In hadronic reaction, it's different. You have proton in the initial state and different state in the final state. So it's off-diagonal diffractive tradition, and it makes huge difference regarding the absorptive corrections. In the first case in DIS, you don't have them. Here you do have, and it also frequently called rapidity gap survival probability, because in diffraction scattering, off-diagonal diffraction scattering, you have at CDF, for instance, you have huge rapidity gap where you have no particles, but you have spectators. Other components of the proton can interact inelastically with the target and will fill the gap with hadron, so will kill your diffractive channel. And survival probability to have no such interaction, suppresses the cross-section, and this was explained why it's down. But anyway, this is an obvious breakdown of such factorization in hadronic collision, and later I will show that there is much more important physics beyond that. It's not just survival probability. Okay, now, as I said, the only process which was strictly proven to be related to deep inelastic scattering via factorization theorem is the Brillouin reaction. And let's check why diffraction is broken with Brillouin. First of all, notice that radiation of heavy photon, which is abelian particle, it does not interact, is not possible in forward direction. Forward direction means transverse momentum to the target is zero. For a simple reason. For diffraction, diffraction was nicely interpreted by Gut and Walker many years ago. It has a pretty good intuitive interpretation. You have a wave packet, your initial beam, which is a combination of different Fock components, and you can choose these components to be eigenstates of interaction. So each component goes to the same component. And if all such eigenstates interact equally, you will never produce any diffraction because you have wave packet and the combination of different eigenstates is preserved by interaction. You have the same amplitude for all of them. So you will get the same wave packet, which means elastic scattering. To get inelastic diffraction, you need difference between different components. However, here, the presence of photon in the Fock components of the quark does not change interaction because photon does not interact. So this means two components, bare quark and quark plus photon, interact equally. In principle, it works only in forward direction, I mean this vanishing cross-section, because in forward direction you have to integrate the amplitude over impact parameter, and then the dipole cross-section is equal, cross-section vanishes, the same for any abelian particle gauge boson, Higgs radiation. And according to Gut and Walker, the diffractive cross-section, as I mentioned, comes from the difference of interaction cross-section of two Fock components. One does not have any photon, it's just, for instance, hadronic dipole of big size. And another one has a highly virtual photon, which makes a small kick to the target, to the quark. And the difference gives you the cross-section of diffractive dissociation. Not cross-section, the amplitude, diffractive amplitude. And if you look back to the diffractive amplitude in deep inelastic scattering, it's proportional to the small hard separation R squared. Here, if I take, for simplicity, R squared be heavy in both, I will come up with small r times big R. So instead of R squared, I have R. And it changes the whole interplay in the table which I demonstrate. So I showed that diffraction is dominated by soft interaction. Here, not anymore. Diffractive Brillouin radiation is dominated, is not dominated by soft. It's like inclusive in deep inelastic. It's 50-50. So you have hard and soft contributing at the same footing to diffractive Brillouin. So the physics changes. And also, this form includes all absorptive correction. You don't need to add here Savile probability. And I just want to show some results of this calculation. So this is fractional diffractive Brillouin cross-section over inclusive Brillouin cross-section at different values of Bjorken X1 and for different scales, for different dilepton masses. And you see it's pretty unusual behavior. I demonstrated that in diffractive de-Young such a ratio is q squared independent. Here it does depend. It steeply rises with m squared. On the other hand, it's steeply falling with the collision energy. And I don't have time to explain, but it comes actually from the saturation effect, which is nowadays very popular. And this also shows absolute cross-section for diffractive de-Young production and W and Z boson production. This is also m squared distribution, so de-Young is falling, gauge boson has a peak. And in this case, we don't have data for diffractive de-Young so far. However, we do have data for diffractive gauge boson production at the tevatron. And here we compare, this is parameter-free calculation, I remind you, and it describes pretty well the data. So maybe I have 10 minutes, even 5 probably. I have to skip Higgs-Strahlung, which is in many respects very similar. Also, some calculation was done for Higgs production from intrinsic heavy flavors. And now I want to say a few words about specific features of gluons, which we observe just in soft diffraction. As I said, diffractive gluon radiation corresponds to so-called triple Pomeron contribution in terms of radio phenomenology. And experimentally, we perfectly can discriminate between gluon radiation and no radiation. If we have no radiation, it's so-called PPR term, and in radio phenomenology, the m squared distribution is 1 over m cubed. And if you radiate a gluon, because gluon has spin 1, the tail at large masses is much bigger, it's 1 over m squared. And this is how making fit to diffractive mass distribution, people discriminate between these two contributions. So I should say this is a maybe unique case where you can experimentally strictly detect radiation of a gluon. In inclusive process, it's nearly impossible. So if to treat, excuse me, go back, if to treat in terms of triple regio, you see here you have proton Pomeron collision elastic scattering or total cross-section of Pomeron proton. It's like Engelmann-Schlein, however, we don't make any hypothesis here. This is just Pomeron proton total cross-section, which I am not going to use as information for other reaction. I just wondering how big is Pomeron proton. What would I expect? Pomeron is a gluonic exchange, so it's kind of glue-glue dipole. And how strongly glue-glue dipole interacts with a proton. What we know from HERA data is QQ-bar dipole. And obviously, glue-glue dipole should interact stronger. Roughly, if I use this Casimir factor 9/4, if I take pi QQ-bar dipole cross-section 25 millibarns, so I have something like 50 millibarns. This is what I expect. And it was measured, when you measure triple Pomeron term, you can directly extract Pomeron proton cross-section from data. And the result is shown here as function of the invariant mass squared of the final excitation. And you see at large M, it goes down and probably is leveling off at the value even quite smaller than 2 millibarns. I put here 2, but it's even smaller. And this is dramatic disagreement with this simplified expectation. Nevertheless, the difference is so huge, one needs to invent some explanation. And the explanation is pretty obvious. If you have glue-glue dipole, we expect is bigger than QQ bar dipole cross-section only if they have the same size. However, if I am free to assume that glue-glue dipole is much smaller, the cross-section will be much smaller. So from this disagreement, the only outcome, I think, is to say that typical size of glue-glue dipole is much smaller. And then for any reason, and probably it's non-perturbative physics, which we did not include in this expectation. So this means if we look at the, at the snapshot of a highly energetic photon, you see 3 valence quarks and not gluonic field spread all over the proton. It's located in some spots of small size, so we have 2 scales inside the proton. Big scale, which is confinement radius, and much smaller size, which fitted to diffractive data should be about 0.3 Fermi. And it goes along with models and calculations based on non-perturbative dynamics. First of all, calculations on the lattice of glue-glue correlation performed by Piso group, they found the radius, correlation radius, very small, 0.2, 0.3 Fermi. Also, instanton models give the same size, 0.3 Fermi. So here, at this point, I'm not going to discuss where it comes from. I just say from non-perturbative effect, but this is experimental observation. Without this small scale, you cannot describe this data. And there is actually a long list of other experimental evidences that there are 2 scales in the proton and in all hadrons, so a scale which is much smaller than the confinement radius. And the last point is nuclear shadowing. And nuclear shadowing is tightly related to diffractive physics. It's nearly the same. Let me start with different interpretation of nuclear shadowing. One interpretation is pretty popular, is interpretation for highly energetic proton moving, a highly energetic nucleus moving with large energy compared to its mass. And let me start with a simplified model of the nucleus. We assume that there is no, in the rest frame, there is no overlap between nucleon bubbles and internucleon separation. It's just to simplify the whole picture of coherence. So this means that in the rest frame of the nucleus, they don't talk to each other, they don't overlap. Now we make a Lorentz boost, and all distances between nucleons contract to by a factor nucleon mass over its energy. However, the longitudinal size of each nucleon is also contracted. So if they don't talk to each other in the rest frame, they will not do that in the boosted frame. However, as I said, the parton cloud of these nucleons is not Lorentz invariant. The parton density rises with increasing energy, and the Lorentz factor for partons at small x is quite different if you have a mass, nucleon mass over energy for the large x region. Here is x at this cartoon.